This video is part of the book Statistical Modeling with R that I wrote in 2023 and was published by Oxford University Press. Today I'm going to talk about GLMs when the response variable is a proportion, starting as usual with the explanatory data analysis to be followed by the frequentist model fitting and finishing with the Bayesian model fitting. The codes and data to run this analysis can be found in the website shown in the screen. A response variable having proportions can arise either as calculated from counts as a proportion of one of two alternative outcomes of an event divided by the total number of observed events, or from a continuous measurement. When proportions arise from counts, they could denote two things. One is a binary outcome. In this case, we could model the response variable as a binary GLM for group data. Please see the book chapter and the videos where I discuss that. And this can only be done when it's feasible, and feasible here means when all the rows in the data frame have the same values for the explanatory variables. Alternatively, it can come from a polytomous outcome, that is, several outcomes, more than two, that exclude each other. And this should be modeled either as a multinomial or, when appropriate, as an ordinal GLM. I'm not going to talk about either of these two models in this set of videos. When proportions arise as continuous measurements, again they could denote a binary outcome. This should be modeled with a GLM with a beta distribution. This is what we are going to do here in this video. And alternatively, it could come. These proportions can be a set of proportions adding to one, and this should be modeled with a GLM using the Dirichlet distribution. This is a probability distribution that is a generalization of the beta distributions when there are more than two alternative outcomes whose proportions we measure. I point out to you to this very clear and recent article by Dunn and Weldon where these things are neatly explained. So here, as I said, we are going to consider just the case when the response variable is a continuous measurement of an underlying binary outcome, and this, as I mentioned, would be modeled with a beta distribution. The beta distribution applies to values of a response variable that are real numbers between 0 and 1 in the unit interval. And this probability distribution is very old, was originally defined in terms of two parameters, A and B, depending on the book, but has been reparameterized in terms of two parameters, its mean, and a dispersion parameter phi, that governs the relationship between the mean and the variance of such response variable. So the beta distribution is extremely plastic. It has the very different shapes that range from uniform to an inverted U, a U, an ascending or descending exponential depending on the two parameter values. The beta distribution, formally speaking, does not belong to the exponential family. Please see the chapter and the videos shown in the screen, but is close enough such that when we estimate the dispersion parameter phi by means other than the likelihood, maximum likelihood, this allows us to use the formalism of GLM. These GLMs use a log-link function. So the data analysis in case relates to studying the effect of sheep grazing and other landscape variables on total plant cover in Argentinian grasslands. So I start again by importing the data set. The data set includes the response variable total cover and the grazing pressure of the sheep. This was measured in three areas of different primary productivity, and here are the landscape variables that I alluded before. So by standardizing these explanatory variables, we can compare their relative effects on the mean of the response variable on the scale of the model link function. So here I simply create a data frame that contains the scaling of the numerical explanatory variables, so in order for them to have zero mean and unit standard deviation. And this data frame also contains the response variable, and the categorical explanatory variable. So we are going to use as usual, the cumulative distribution function and the QQ-plots to compare three candidate distributions to model these response variables. After fitting the distributions, here are the plots, and what we can see in the plots is that the three distributions are essentially identical or non-distinguishable by eye. So because of that, I calculated the AIC for the three distributions. The AIC for the three distributions are essentially identical. This is not a decisive difference in the AICs of the three distributions. So the conclusion, tentative at this point, is that we are going to use the beta distribution, and the main reason to use the beta distribution is that we can use a logit function such that after estimating the parameter values, the inversion of the logit link function would guarantee that the predicted probabilities would be real numbers between 0 and 1, as they should be. So the statistical model is that the response variable follows a beta distribution with these two parameters, and the logit of the mean is a linear combination of the explanatory variables. Let's examine then the relationship between the response and the explanatory variables. Here is a large set of plots. In the diagonal we had the density plots with different colors for the different levels of parameter productivity, high, low, and medium, alphabetically ordered. And so we have here that two of the explanatory variables, number of patches and patch size, are negatively correlated. They have a very high negative correlation, and therefore I'm going to exclude the number of patches from the model. This choice is by and large arbitrary. If you work in landscape ecology, for instance, you may choose the variable to exclude on a different manner that I did. The lower row shows us the relationship between the response variable in the vertical axis and the explanatory variable, different explanatory variables in the horizontal axis. What we see is that the relationship between grazing pressure and total cover differs. Notice that the slopes here shown differ depending on the level of parameter productivity, and this can also be seen for the patch size. So therefore we are going to include the interaction between productivity and grazing pressure and productivity and patch size in the model. So the frequentist model fitting includes these interactions between these explanatory variables, as I just mentioned, and the single effect of interpatch distance. So this notation here simply says that the model will include the single effect of grazing pressure and the single effect of productivity and their interaction. This is a shorthand of writing this. And this model will be fitted with a package GLM-MTMB that allows including, and this is done in the book but not in this video, explanatory variables on the dispersion parameter, the phi parameter of the beta distribution. I fit the model, and the model contains the following parameter estimates by maximum likelihood and with their standard errors, and this p-value simply says whether these fitted parameters are significantly different from 0. So the level of productivity are 3, high, low, and medium, and high alphabetically was assigned as the reference level. So the intercept corresponds to the logit of the mean of the response variable when the numerical explanatory variables are 0 for the high level of productivity. So prod low and prod medium corresponds to the differentials of intercepts between the logit of the mean of the response variable for high and the logit of the mean of the response variable for low and medium. This difference of intercept, one of them happened to be statistically significant. Grazing pressure here indicates the partial slope of this numerical explanatory variable for the reference level of productivity. And here grazing pressure low and grazing pressure medium corresponds to the differentials of intercepts of the other two levels between of grazing pressure and the logit of the mean of the response variable for the other two levels of these numerical explanatory variables. This p-value here says that these differences of slopes happen to be statistically significant. So because the partial slope here are the effect of changing one standard deviation of each numerical explanatory variable on the logit of the mean of the response variable. We can see, for instance, that for the reference level of productivity, which is high, changes in one standard deviation of patch size has a much larger effect than changing one standard deviation of grazing pressure on the logit of the mean of the response variable. So here is the reference level of grazing pressures, and the two. Here is the slope of grazing pressure for the reference level of productivity, and here are the differentials of slopes for the other two levels of grazing pressure for the other two levels of productivity, and likewise, here is the partial slope of relating patch size with the logit of the mean of the response variable for the reference level of productivity, and here are the differentials of slopes for the other two levels of productivity for this numerical explanatory variable. By fitting an alternative but identical model, we can calculate directly the slopes and intercept for each of the response variables. For each of the explanatory variables, here we see that the differences of the actual intercepts for each of the three levels of productivity, and here we see the slopes of grazing pressure for each of the three levels of productivity. Here, this is directly the slopes, not the differentials with respect to the numerical reference value. From this, we see that changes of one standard deviation of grazing pressure has a tenfold higher effect and different signs when productivity is low compared when productivity were low and medium. So we can also compare the effect of one change of one standard deviation in each explanatory variable for each level of productivity. This model explains 71.7% of the deviance of the response variable, which is a pretty high percentage. So in order to assess the goodness of fit of this model, we use the package Broom mixed, because this is what we need for a model fitted with the package GLMM. So we first gather the input for the analysis, then we calculate with the command simulate residuals of the package dharmas, the Dunn-Smyth residuals. These residuals are converted to have a normal distribution and put into the original data frame where we had the residuals. So these transformed Dunn-Smyth residuals will only have normal distribution when the model fits well to the data. So here are the plots. So to start, in the plots A, B, D, and E, we see the relationship between the residuals and the fitted values, and the relationship between the residuals and each of the three numerical explanatory variables. By and large, in these four plots, we see a random scatter of values without any discernible trend. This line of points here of grazing pressure simply is because all these sampling points have exactly the same value of grazing pressure. This is just due to the values of these numerical explanatory variables and should not be overinterpreted. Likewise, we see here in these box plots, we see that the median of the residuals for each level of primary productivity are all very, very similar and close to zero, and that the variation, as indicated by the width of these boxes, are all pretty similar, which is a sign of a good fitting model. Now commenting the plot C, this QQ plot shows that the majority, but not all, of these transformed Dunn-Smyth residuals seems to have a normal distribution, which suggests that all in all, these 6 plots that the model has a very good fit to the data, or at least very close to excellent. So in order to communicate the results, we could show a table with the parameter estimates. This could be transformed into a plot, but it says this is probably less interesting than showing the conditional curves with the obtained with the package ggeffects. So these conditional curves show the relationship of each explanatory variable with the response variable by keeping the other variables, the other explanatory variables, to 0, that is to their mean values. Notice that here is for grazing pressure, here is for average patch size, while keeping grazing pressure and interpatch distance to 0. And so please notice that the range of the values in the vertical axis are different for each of the plots. And here is the single level of productivity, which is of little interest given that productivity has interactive effects with other numerical explanatory variables. The Bayesian model fitting, the statistical model is the same as was mentioned before, with a logit link function. So here we see all the parameters that we need, whose priors we need to define. Here are the intercept and all the coefficient class B, reflecting either different differentials of intercepts, differentials of slopes, or slopes for the reference value of productivity. This will all determine the mean of the response variable in the scale of the link function. And the other coefficient phi, the other parameter phi, corresponds to the dispersion parameter of the beta distributions. I'm going to define these priors on the logit scale. And using that, I'm going to fit the model, which simply has the formula that was shown in the previous slide, indicating the beta coefficient. We are going to use a link function, and here I'm just showing this because in this model, like in this package VRMS, we could also include explanatory variables for the dispersion parameter of the beta distribution. This was actually carried out for the Frequentist model fitting and for the Bayesian model fitting in the book, but not shown here for the sake of brevity. As usual, we put the priors that we have selected, that we have modified from the default priors, 3 chains, the number of iterations, and a set of parameters suggested in a previous fitting of the model that suggested that the chains had not converged. Now let's look at the results, and the results here show the marginal posterior distributions of the model parameters on the logit scale for all the parameters except for the phi, which is the dispersion parameter of the beta distributions, and the metrics of the convergence of the Hamiltonian Monte Carlo algorithm. To start with the latter, we see that the r hat values are all very close to 1, and that we have plenty of values, plenty of nearly statistically independent estimates for most of the parameters. Here we have the posterior distributions, the marginal posterior distribution of each parameters, whose interpretation is exactly the same that was shown before for the Frequentist model fitting, and for the sake of brevity will not be repeated again. But you could apply the same logic and reasoning that we did for the point estimate, maximum likelihood point estimates of the parameters. You could apply it to the mean of the posterior distributions of these parameters. And again, because the explanatory variables were standardized, their values of the mean posterior distribution of their slopes could be directly compared, as we did before. The posterior distributions, we can see that the posterior distributions of all parameters converge for the 3 chains, suggesting that the convergence of the algorithm shown by the r hat value. With respect to the autocorrelations, we see that for several of the parameters, we have a relatively high 0.4 autocorrelations for the 3 chains, and some one suggestion to improve this that was not carried out neither in the book nor here in the video is to set the thinning rate of 3 or higher in order to make the computer work harder, that is to obtain more estimates, and only taking a fraction of those sample parameter values retained in the chains. In order to assess the goodness of fit of the model to the data, we are going to use, as usual, the Dunn-Smyth residuals that in this Bayesian model is obtained with from the posterior predictive distribution. Here is the posterior predictive distributions of this fitted model, and with this posterior predictive distribution, the command create dharma of the package dharma, we obtain the raw Dunn-Smyth residuals, and these raw Dunn-Smyth residuals are going to be converted into normal distribution only when the model fits well. So then we create a data frame with all the data necessary for the residual analysis, and this includes the converted Dunn-Smyth residuals, the explanatory variables, the fitted values, the Pareto K coefficients that will tell us the importance of each point on the posterior distributions of the model. And we also have that this Bayesian model has explains 98% of the variation of the explanatory variable, which is a pretty high and almost suspiciously good value. So here are the plots, and we see in the plots A, B, C, A, B, D, and E, more or less a random scatter with the same point that I alluded before of this line of value of the grazing pressure that I just explained for the Frequentist model fitting. These points, these Dunn-Smyth residuals are very close to have a normal distribution for most of them, and that we see that for most of these, the Pareto K coefficients for all the points, data points, are all in the all but 4 are in the very good range, and just 4 values are just in the good range. Perhaps we could even select these 4 values, refit the model without these 4 values, and see the importance of these 4 values on the posterior distributions of the model. With the posterior, we can also, with the posterior predictive distributions, we can obtain the PP checks, and we can obtain the PP checks for the density curve of the response variable here in black, and in gray are the 1000 density curves obtained from the posterior distribution. We can also see how well the model predicts the average plant cover, and we see that the model, like for the density curve, the model predicts the observed value as a typical value of the posterior predictive distributions. Now we're going more finely here, and we see that for each point we see in a small black dot the observed value, and the gray dot is the mean of the posterior distribution for each point, and the interval around each point corresponds to the credible 95% credible interval. We see that for most of the points, with few exceptions, the model happens to be able to predict very well the observed values. If we now go ask the question of how well the model predicts the maximum plant cover, depending on the level of primary productivity, we see that the model is less able than for the other features that we have just shown to predict the observed values, the observed maximum value of plant cover for different levels of primary productivity. So every statistical model will at some point break when we ask for a difficult feature to predict, such as the maximum, the minimum, and the extreme values. So this is extremely useful when we are going to use later the model in order to make decisions on an applied or a specific empirical context. The conditional curves, we obtain a set of conditional curves, conditional effects, actually 6 of them, and we can select which of these conditional effects we want to illustrate, and we show here just the interaction between grazing pressure and primary productivity, the patch size, which is this one, the patch size, the interaction between patch size and productivity, and the interpatch distance. Again, we see, please notice that the range of the values in the vertical axis are different for the three plots. We see the relationships predicted by the model that could be transformed into a commented output of the fitted Bayesian model. So in this video, I have explained GLMs for when proportions are the response variable, starting with the exploratory data analysis that was followed by the frequentist model fitting, and finally we had the Bayesian model fitting. I hope you found this video interesting, and I'll hope to see you soon in a coming video of this series. Thank you for your attention.